for these intramolecular reactions, we want to make either a either a 5-membered ring or a 6-membered ring to be more favorable. Can the other size rings form? Yes, absolutely they can, but the preferred ones are 5 or 6. That would be the preferred combination. Okay, so I don't know which ones we already did, so if you've already done this, I'm sorry.
Bye.
So let's say we have this compound being heated with sodium hydroxide, what would it create? So think about it. First try for 5 or 6 membered because those are more favored. Same thing. And same reagents, I'm not writing them over and over again, but those are the same. Figure out something. So what do you think in this case? 5 or 6? Where would the alpha carbon be? Where would the enolate? Okay. There are several alpha carbons, right? That's alpha, this is alpha, this is alpha. Which alpha carbon could lose a proton, make an enolate, and then cyclize intramolecularly and produce the product? Which one would be the best one? Louder? So here's how the process works. Let's say this is the one that you're thinking about. When you say middle, do you mean that one?
Yeah.
Okay, so then let me call it carbon 1. If that goes and attacks the other, right? What would be the size of the ring?
4. Oh.
Right? So not favorable. So that's how you figure it out. Okay, if that were the case and it went and attached here, then that will give us a 4-membered ring. Okay?
The first one?
So exactly. So that's how we process it, guys. What if it were this carbon that made the enolate? Because that's alpha. What if we deprotonate it from there, but then it goes and cyclizes here? That's 1, 2, 3, 4 again. Right? Not favorable. So you were saying this one? If this one made the enolate and then it goes and cyclizes with the other carbonyl, that's 1, 2, 3, 4, 5, 6-membered ring. So again, choose, if possible, 5 or 6 is preferred over any other size. So yes, absolutely, in this case, it would have to be that one. So what's the product? And we are heating also, so we are indicating condensation. So alpha, so it's a 6-membered ring, right? let's say this is carbon 1, then that's carbon 2, 3, 4, 5, 6, agreed? And what's on carbon 6? There's a hydrogen.
Yes.
So if the condensation happens, we're going to make a double bond there because we're going to lose water. Please do make sure you can write a mechanism. It's the same mechanism that we wrote on Monday. Making an enolate, cyclizes, makes the aldol product, the aldol alcohol product, and then the alcohol product goes through E1CB to create the double bond. So please do make sure you can write the steps. Do we want to write it one time or we guys got it? What do you guys say?
One time.
Let's do it one time then, just one time. Step number 1. What do you guys say? Step number 1.
The base takes the alpha carbon.
Proton,
hydrogen.
right?
Yeah.
You have to make the enolate. Exactly, the base takes this and creates the enolate. Whichever resonance structure of the enolate you show, that's up to you. But you have to make the enolate first. And it is the enolate. What does that do now?
Attacks the carbon.
Right. The nucleophile attacks the electrophile. That's how the ring cyclized. Right? That's how the intramolecular reaction happened, which ends up creating a 6-membered ring where the ketone has recreated. And what about on carbon 6? We have O minus. Agree? What next? Anybody? This should take a proton from water. So it does make the aldol reaction product, which is a beta hydroxy ketone or beta hydroxyaldehyde. So you are making that first. That's your beta hydroxy ketone, the aldol reaction product. Now this goes through E1CB. So what's the step for that? How is this going to carry out E1CB? Anybody? Please note, it's all in basic environment.
We're going to take alpha hydrogen.
Good. Which side would be the better side to take from? Because there are 2 of them.
Next to the hydroxyl.
Exactly. So the base comes in, takes proton, creates an enolate again. It's still a ketone, it can make an enolate. And that's the conjugate base, E1CB. CB means conjugate base, meaning someone took a proton from it. So now you have the conjugate base. And this conjugate base then undergoes, am I missing? No. Elimination reaction to recreate the hydroxide and make the alpha beta unsaturated aldehyde or a ketone. Does that sound okay, everybody? Cool. Can you please go ahead and tell me what the products would be? Feel free to go to the board, draw them out. I don't have an ink. Please feel free. There was one you were showing me the other day, honey. Was that from the book?
Yeah.
There's one from the book Fun was showing me. Maybe we should try it out. Do I have the double bond O's in the right place?
I don't think so. The one on top should be in the middle.
Middle?
Yeah.
Okay. Oh, they're both in the middle?
Mhm.
Okay. Oh, wait. Is that right? Like that?
Mhm.
Something like that? Okay. What's going on?
Messed it up for me.
Maybe we can get two products. Looks like in this case, we might end up with two products. Say again?
Is there a preference between?
Let's draw them first and then see if there might be a, thank you.
Yeah.
Oh, now you put it right out of my reach. I will have to climb. No, don't worry. Finish. So 1, 2, 3, 4, 5. Okay, so that's one.
And the other one would be.
Let's draw this first. Let's draw this and see if it's. So make a 5-member ring first and pick one of the carbons to be 1, whichever. Okay, so then where is 2? What should that be? Just good. 3, 4, 5. What should 5 be? Okay.
So the other one would be here, right?
Mm-hmm. And
where this goes.
exactly. Which carbon is that on? What carbon is it on, Camilla? Oh, there you go. Okay, so that's one combination.
Oh, that's right.
I think another is possible. 1, 2, 3, 4. Yeah, another is possible. Not 6. I think you counted it wrong. But where is it attacking though?
This one? If we do it this way?
Okay, sorry, I'm not saying things very clearly. Where is your carbon 1? Go ahead, write it
From here or from my new one?
for the new one. Okay, so that's your alpha carbon, which is the enolate carbon. Where is that going to attack?
Here.
Yes, so your connection is between those two. There you go. So it's still a 5-member. Now make one carbon 1, whichever one, doesn't matter. Okay. There you go. Perfect. So Jasmine, to answer your question, here are the 2 products, and this is for everybody. If we had to guess which of those products might be the major product, which one would you guys choose?
Right one?
And right, you mean the second one?
Yeah,
Why?
because it's the alkenes more.
That's it. It's the alkene stability. It's the more stable, because everything else is the same, right? So it's the alkene stability that will differentiate that product and make it more stable, hence thermodynamically favorable. Does that make sense, everybody?
I did it wrong.
Which one?
What I was doing.
Oh, okay.
Did we do? No.
It's symmetrical. If it's symmetrical, it's just one. Okay, cool. Please practice the mechanisms. Make sure, do it a few times, write it a few times, push arrows. Remember that if it's acidic, you've got to make sure everything is either neutral or positive. If it's basic, then you can have negative charges. Otherwise, you can't have negative charges.
Oh.
Oh, I see. You're fine. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Cool. Okay.
No, you got it.
Oh.
Do you all agree? Do you all agree? What a silence today. I think it's absolutely right. Now, why did the second one, why didn't it create a double bond even though we heated it with sodium hydroxide? Why did it not create a double bond? Exactly. It has only one alpha proton, so it cannot do the E1CB. There's only one of those, right? It cannot do, it can stop here, but then it can't go forward because it doesn't have another proton to donate. So it stops right there. Oh, Camilla's on what's the phrase?
No.
Roll, yes. Camilla's on a roll. Perfect, okay, cool. Yes, you can. Yes, you can. 7? How 7? Maybe that's the wrong combination you're thinking about.
Wait.
And as I said also earlier, that 5 and 6 are favored. That doesn't mean that you can't get other sizes, it's just that in preference, 5 and 6 are favored.
So it can be 7.
It can be if that's the only option, but here, can't you have a 5? I was counting 5, and then the other one becomes a 7. If one is a 5, then the other one becomes a 7, that's fine. Go ahead, take a shot at it.
That's just a 7?
Whatever you. Ooh, but it's not finished, is it? Are you done drawing the product? There is a total of 10 carbons, you only showed 7, I think. Someone please, anybody? No, that's a great, you got it to a good start.
Using 3, right?
Where's your carbon 1? The way you've numbered it, where is that? So where is 2, 3, 4, 5, 6, 7? Okay, so that's 7, right? What's connected to 1? What is, which you haven't accounted for yet? So 3 carbons. Where are they?
So 10 will be, oh, 0,
But absolutely, absolutely. I mean, basically, I like it, but it's okay. Exactly. Those are right there. 7, 8, 9, 10. I mean, 8, 9, 10. So you were counting it this way. I was counting it as 1, 2, 3, 4, 5. That's a 5-number ring, but then the other one ends up being 7 anyways.
I was thinking about going that way, but for some reason I was telling myself I have to pass this one in order to get.
Doesn't matter.
Okay.
But the point is, the product will be the same no matter how you count it. Because if one ring is going to be 5 carbons and the other one, which is fused together, has to be 7. So it doesn't really matter how you count it.
The other one like
But-
have double bond here and then.
No, it'll still be the same. It'll be exactly the same. Exactly the same. So, can rings be 7? Yes. Can they be 4? Yes. But 5 and 6 are preferred. That's the point. Does this make sense, everybody? Intramolecular aldol condensation. Cool. Then let's go to the next reaction. And that is similar to aldol, but a bit different because it's not aldehydes or ketones, instead esters. And that is called Claisen condensation. So idea is the same, logic is the same, but different outcome because instead of using aldehydes, ketones, we are using esters. Now, Claisen condensation, as I said, uses esters. Again, 2 esters will react with each other. They need to have alpha hydrogen. So let me say, for example, one of them is this, OMe or OET, those are the simple ORs. So one of them will make an enolate because there is the alpha hydrogens and react with itself in exactly the same way. So I'm just going to draw another one. Whether it's the same or different, we'll talk about the details as we go through the process. And they will, this is a 2-step process, and I'll tell you why when we write the mechanism. First step is using the base. Now the base we choose in Claisen condensation to avoid other things from happening. We don't want complications, we don't want other paths to follow, we don't want the esters to be hydrolyzed or to be trans-esterified. So we choose the same base. We match the alkoxide with the OR in the ester. That way we can ensure that nothing else is going on. And the second step is we got to protonate. And again, as I said, we'll write the mechanism and understand this really well. The outcome in this process is an alpha. So this is the new bond. Alpha, sorry, not alpha, sorry, beta, not alpha, beta, keto. Did I miss? Yeah, I did. A beta keto ester. That's it, that's your product. Will be a beta keto ester. Okay. So let's look at a specific example, then we'll write a mechanism. We'll do that a few times, a couple of times, and try and get comfortable with Claisen condensation. Let's start with something simpler, which is ethyl acetate. No, that's simple. Okay, that's ethyl acetate is this. And if it is reacting first with sodium ethoxide, please again, the OET, the OR of the base is the same as the OR of the ester to avoid other things from happening, such as hydrolysis of the ester or trans-esterification of the ester. Can you please tell me what the product would be, and then we will write a mechanism. So what would the product be? 2 of these are going to connect with each other using, so let's say if one of them is using its alpha carbon, It's creating a bond in that position, right? The alpha. The other one is using its carbonyl, C double bond O carbon, just as before, C double bond O carbon. So if the second one is using the C double bond O carbon, so that's the ketone and the CH3. The OR is gone, as you notice. We lost one of the ORs. But we'll write a mechanism. That might actually remind you of something we've seen before. What? What does that look like? Isn't it the acetoacetic ester we used in those syntheses? It's basically created from failed condensation of ethyl acetate. But anyways, let's write a mechanism. Let's try and understand how is this happening. So what do you think will be the first step? Don't think too hard. Okay. Enolate. The base takes proton alpha position, makes the enolate. What would be the next step? The enolate the second molecule. Which where would it attack the second molecule? The C double bond O. Just exactly like aldol, right? The enolate attacks now. As we said earlier, this was a couple of weeks ago, there's one thing that the acid derivatives have which aldehydes and ketones don't have. Does anybody remember what that is? Does anybody remember what is it that esters have which aldehydes and ketones don't have?
Leaving groups.
Exactly. And that's the difference here. Till then everything is exactly the same. So if that's that, so O minus, OET, and methyl. So what is it that esters have that aldehydes, ketones don't have, which is why aldol is different from Clasian? These guys have a leaving group. And you've seen this before. O minus comes back and kicks out the leaving group. You've seen that before. Isn't that right? What does that create? When that happens, what do we get? Did I lose a carbon? I think I lost a carbon. Hold on guys, I think I'm a carbon short here.
Yeah.
If you were grading me, hopefully you will take off a point right there, won't you?
You're
No,
missing one
I'm
carbon.
Oh, come on, I'm not that generous. Don't expect that from me though. Yes, I lost a carbon. Where did my alpha carbon go? Sorry about that, guys. It should be one more. Sorry about that. Yes, I lost a carbon there. There we go. Right? This carbon is here. Should have that there. And then this, of course, kicks out the leaving group. So, do you agree? Everybody agrees so far? Okay, so then I have a question. Isn't that the product?
Yeah.
Then why do I need this? I already got the product, why do we need the second step? There's nothing to protonate there, at least not that I can see. So why do you think we need that second step? Neutralize what? It's already neutral. It's already neutral, right? There's no ion here. Okay, then let me ask you another question. Do you think this can survive?
No.
When there is when there's ethoxide all around? Is that alpha hydrogen?
Yeah.
Right? Does that guy have alpha hydrogens?
Yeah.
Of course, it has 3 here, but I'm not concerned about those. But I'm concerned about these. Which do you think alpha hydrogens are more acidic? Those ones or the ones in the middle?
In the middle.
Way more acidic. Why?
State
What?
resonance.
Exactly. Why? Why?
Oh.
conjugate bases.
Yes.
Exactly. Here you're delocalizing over 3 atoms, but here you're delocalizing over 5 atoms, way more stable conjugate base. And so the point is, step number 1 doesn't end here. Yes, we get the product, but the product quickly, because there's ethoxide in this system, loses a proton, one of those middle ones. Those are very acidic, very acidic. And therefore, step number 1 ends here. Step number 1 ends there. So why do we need step number 2? Anybody?
You will get a, I wanna say you will get an enolate and then it will do tautomerization.
Exactly. You can do that, or if you're lazy like me, I'm just going to be like, okay, fine, the proton goes there, ultimately it goes there, of course. Because, so please keep in mind, the first step cannot end there. The first step will lose a proton at the end, the product will lose a proton, there's no way to prevent it because those are very acidic hydrogens right there. So this is where step number 1 ends, and therefore we need to put the proton back to create the product. Does that make sense, guys?
Mm-hmm.
This is Claisian condensation. If you really think about it, it's kind of like aldol. The difference is we have a leaving group with in this case, but aldehydes ketones don't have a leaving group. That's why the outcome is different. Everybody okay?
Quick question, would it matter if you showed that
No,
enolate
not
going to
at
the
all.
other side? Okay.
No, exactly, it's a resonance structure. So what
right,
Jade is
right,
asking is, instead of showing this, what if we showed, isn't that what you're asking?
Yeah.
They're all resonance structures, and resonance structures don't exist, the hybrid exists, so who cares? Pretty much, yeah. But does that make sense, everyone understands this? Now how are these two pieces coming together? Same way. The alpha carbon of one and the C double bond of carbon of the other, but that is losing the OR. We are losing the second OR in this process. That's why you end up with a ketone. Let's try it a couple more times. So, please. So what base would you tell me to use in this case?
Methoxide.
Because we are matching that. So whatever OR is, make sure you're using the same alkoxide to do the reaction. Please, go ahead. Tell me. First, let's draw the product, then we will quickly draw the mechanism once again, and then we look at some other examples. Is that correct? Just trying to color coordinate to see how those are coming together. Hopefully
Yes.
that helps and not confuses more. But you guys agree?
Yes.
One uses its alpha carbon, the other one loses its OR when the connection happens. Okay, let's write a mechanism. So, step number 1, what do you guys say?
Add the methoxide.
And what will that do?
Make the enolate.
Makes the enolate by taking the alpha proton, okay? And then what will the enolate do?
Attack another
act as a nucleophile and attack another one of itself. Okay, so the alpha carbon attacks. What does that do? So O minus, OMe, and then, did I draw that correctly? Yes? Is that okay, everybody? Okay, what is this going to do? It's going to kick out the leaving group, because there's a leaving group there. When the leaving group is kicked out, that gives us the product. Does it?
No.
No. What happens to that guy?
Loses an alpha hydrogen.
Because there is still, especially this one, we are only worried about the hydrogen in the middle because that's very acidic. There is that hydrogen right there. It cannot survive. In a basic environment, that cannot survive. It will be lost. So this time I'm going to make the other, oh, it's the same. Create the enolate. Doesn't matter which resonance structure you show of the enolate, because resonance structures don't actually exist. Agreed? And therefore, second step. Now, that's where it stops. So we have to add a 6 molar HCl as you've done in your labs, right? The extraction at 6 molar HCl. Let's put the proton back. The proton basically goes back to the alpha position. It doesn't really go back to the alpha position. It first goes to the O, but then that tautomerizes and blah, 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 but who cares? Ultimately, it ends up on an alpha. If you want to write the mechanism of the tautomerism, that's pretty good too. That's going to be like, yay. But it's up to you. Everybody okay?
Yeah.
Everybody okay?
Yeah.
Cool. Then please tell me. What would the product be? Did I lose a carbon
I
again?
think we just lost a methyl in the middle, but it doesn't
Ah,
matter.
no, I didn't. Haha, that's why you guys are looking at me and smiling. Come on. Yes, I did. Okay, what would the product be? Are you going to draw the product? You're right. You keep going. There you go. There you go. Yeah. You all agree?
Do you need?
That's my question. You don't get to ask my question. No, but go ahead, ask again anyways. Ask.
I said, do you need the protein in this one? Because there's no-
Exactly. So there's a reason I didn't write anything on the arrow, and that was going to be the question I wanted to ask you. Do you think in this particular example, we need step 1 and step 2?
No.
Do we need step one, which is of course the base, sodium, something ethoxide, we definitely need that. But do we need step two? Why not?
There's no signal.
Exactly. This one, you don't need step two, because that carbon, the alpha carbon, has only one hydrogen, which the base takes in the first part of the mechanism, and this cannot happen. This cannot happen. So if this cannot happen, because there's no more hydrogen left in that case, well then why do we need acid? It stops right there. Does that make sense, everyone? So, when the alpha carbon has two or more hydrogens, we need both steps. But if the alpha carbon has only one hydrogen, you don't need this. Because there's nothing that will happen with it. Everybody okay? Cool. So that is Claisen condensation. Again, the mechanism is similar to aldol. The only difference is that there's a leaving group which aldehydes ketones don't have. So let's look at crossed Claisen condensation. Do you guys remember crossed aldol? Yes? I will take your silence as yes. So what do you think is crossed Claisen? What's crossed aldol?
When you don't just have one.
You have two different aldehydes and ketones, right? So what is crossed Claisen then? You have two different esters. But once again, practically speaking, this makes sense to do so that you don't have to deal with multiple different kinds of products. This makes, it is using two different esters, but only one that can make an enolate. Meaning, only one that has alpha hydrogens. The other one, the other ester, we choose in such a way that it cannot make an enolate, does not have alpha hydrogens. So for example, do you think this can make an enolate? Can this make an enolate?
No.
Formate ester. No, there's no alpha carbon. Can this make an enolate? No, the alpha carbon is the benzene carbon. Cannot make an enolate. Can this make an enolate? It's not technically an ester, it's a carbonate, but the point is it still has leaving groups. Same ones. Can it make an enolate?
No.
No. So there are lots of esters, these guys such as, these are just example, cannot make an enolate because they don't have alpha hydrogens. So when we do crossed Claisen, just like crossed aldol, we choose one of the esters to be one that cannot make an enolate because it does not have alpha hydrogens. So for example, if I were combining, let's say, ethyl benzoate with first of all, do you think in this case we should have steps 1 and 2 or just step 1? What do you think?
Just
Should we have both the base and the acid step or not? We don't need the acid.
both steps.
Why?
Because there's two alpha hydrogens.
Which alpha are you talking about?
The second one.
That one cannot make an enolate. It does not have alpha hydrogens. It cannot make an enolate. This one can make an enolate, and there are two hydrogens there. Absolutely, therefore, we should have steps 1 and 2. 1 to deprotonate, make an enolate, and then do the rest of the reaction. And the second is the last step where the proton needs to be put back. Can you please tell me what the product would be, and then let's quickly write the mechanism one more time. So So which one is going to make the enolate and which one is going to lose the leaving group?
The second one's gonna make the enolate and the first one's gonna make the.
Good. The second one's going to make the enolate because it has alpha hydrogens, so that means the first one, which cannot make an enolate, is the one that's going to lose the leaving group. So what would the product be? If this loses the leaving group, that's the leaving group. If it loses the leaving group and connects to the alpha carbon of the first one, what does that create? Do you agree? Did I do that correctly? Did I lose any carbons? Okay. Mechanism. Let's do this fast. What's the first step?
Make the enolate.
Make the enolate. The base takes the proton from the alpha position, makes the enolate. Okay. This is, I think you guys are getting the mechanism really well. So after this one, maybe we won't write them again, unless you want to. So please do let me know how you feel about that. What will the enolate do?
Attract
The other one,
the other one.
right? Exactly. The enolate will come in, attack the other one because that cannot make an enolate. So goes there. So this creates a tetrahedral intermediate. And this. Next step, the tetrahedral intermediate will kick out the leaving group. Like we've seen in so many different reactions of esters and other acid derivatives. That's where this was lost, kicked out. What next would you do?
Add the acid.
Not yet.
Oh.
It's neutral. So
Lose the
this,
alpha hydrogen first.
exactly, this is not going to survive because there is that very acidic proton, hydrogen. So it is going to make the enolate again. And this is where the first step will stop. That's where it is. And this is the one where we have to now protonate because we want to put the proton back and create the product. Does that make sense, everybody? Everybody okay?
Yeah,
Yes.
I'm wondering, will you get a mixture because,
Mixture of?
because, like, at the beginning, will
Oh.
it attack itself as well?
Yes, yes, true, yes, absolutely, you will. You will definitely get this guy reacting with itself product as well. So, this one though will be major. Let's talk about why. So imagine you've taken, I'm making up numbers. Let's say you've taken 100 molecules of this and 100 molecules of this. And you've added the base. Let's say even if one enolate ion is created, what it will probably see bunch of these around and some of these around too. I'm just taking it one, but whatever concentration of enolate you've created, there will be likelihood of having more of these around than those around. So the major product will be the crossed. Will there be a minor product of this non-crossed version of Claisian product? The answer is absolutely. You cannot prevent it. Absolutely. Now there are ways of minimizing that. Practically speaking, if you're doing in the lab, there are ways of minimizing the minor product and maximizing the major product. What I would do, to be honest, if I'm doing this in the lab, I will start with this, dissolve it in whatever the solvent is, probably ethanol because that's OET, so I would probably choose ethanol, dissolve it, and add this to that. Because I know sodium ethoxide will do nothing. So now you have this round bottom flask or whatever flask you're using with a large number of those molecules and the base which can't react with each other. And then I will add this drop by drop by drop over a period. So you can manipulate that, and it's all a concentration game to make sure the concentration of this stays larger compared to that. Absolutely, absolutely. Any questions, guys? Okay. Now that you mention it, I'm just remembering when I was doing when I was in grad school, which was so many years ago, there was one reaction that I was working on. I worked on it for months and months and months, but that required me to add one reagent overnight. I had to do it through the night. Of course, I wasn't doing it manually because that will drive me crazy. But there are equipment there. There's what we call a syringe pump. So you set it up, whatever settings needed. I want to add this over 20 hours or whatever it is, and then it manages it. Basically adds drop by drop. So those are possible. Those things are possible. Okay, please tell me. We don't have to write a mechanism here, but do practice at home, please. Please do practice at home. I'm leaving the arrow blank for a purpose, for a reason. So when you draw the product for me, please also write what's needed on the arrow.
Oh, do you want to go to the board?
Yeah. Unless you can write from there, I'm happy with that. Whatever you're comfortable with. Okay, do you guys agree? Everybody agree? Yeah? Okay, please practice the mechanisms at home so that you get comfortable with this reaction and its mechanism. Okay. So if there can be, where did I teach? Oh, it's right here. If we can do intramolecular aldol, do you think we can do intramolecular equation? Why the heck not, is the question. So that is called, just a second, intramolecular Claisian condensation is called Beekman's condensation. nothing but intramolecular. Everything else is exactly the same. It's just happening intramolecularly. Once again, the idea is to make a 5 or a 6-membered ring to be preferred. So let's give that a try. Please. Please tell me what would I get, and do practice writing the mechanism. The first board is Dieckmann. These are not. These are everything put together. All the different kinds of Clausians put together. So the first one is Dieckmann. Does anybody have a product for me for the first one? For the Dieckmann condensation, please go ahead. The rest are miscellaneous condensation. Miscellaneous Clausian condensations. Or not. I guess this is not technically Clausian, but it's the same idea. Do we all agree with the Dieckmann product? These are miscellaneous things. Those are not Dieckmann, this is Dieckmann, that's it. I'm just writing more questions for us. But do you all agree with this? Oh, no, how can it be OET? So you're right with your numbering, but no, remember that it kicks out a leaving group. Well, if it's using the alpha carbon, that's not the leaving group that kicks out. If you think of the mechanism, right? So if you're saying you're making this enolate, right? Because you said that's the alpha carbon. And then this attacks, right? That becomes O minus. And then the O minus comes back, kicks out. So it can't kick out that. It has to kick out the leaving group from the one that.
Yeah, wouldn't that be the one that would be here?
So then where is your C double bond O? Where's your ester?
Oh.
Let's think about it again. Your numbering is correct, your product is not.
Would it be here then?
See? Then where's your ester? Shouldn't there be one ester? No.
Oh.
Your numbering is absolutely correct. But then think about the mechanism as you're figuring out the product. try though. Anybody else?
They go with that.
Do it, I don't see thing. Group consensus is this. There, that's my numbering.
It has to be a beta keto ester.
Because one of us, one of us like not keep theirs, this is leaving group, this is one.
Ooh, the one is not that.
Yeah.
The one is this. So not 7-member, it's 6-member.
Oh, this is
But-
just for me.
Oh, that's
This
just
is
for you.
me.
That's, as long
That's
as.
how I do it, yeah.
Yeah.
Well, how was that one? Yeah, cause the new one, this is how I know what this is one.
Do you all agree?
That's, yeah, I just count the cards.
Everybody agrees? Is everyone able to see it? So once again, step number one, I'm not writing the mechanism, but step number one, the alpha carbon loses a proton, so you make an enolate. The enolate attacks the other one, cyclizes, makes the 6-membered ring, and O minus OET, and this is going to be, right? And then this loses the leaving group, picks up the leaving. That curved arrow looks bad. So the product should be a beta ketone. There has to be a ketone in the beta position. Sounds okay, everybody? The rest of the questions are all equations, different kinds of equations. So we're just thinking about equation because they're esters, although there are a couple of them that are not all esters, but the idea is the same. Concept is the same. So let's see if we can figure those out. And I know some of us here are shy to go up there or say anything, which is fine, as long as you don't have any questions though. As long as it's okay. Okay. Oh, you're not done yet.
No.
Okay. Sorry about that then. Sorry about that.
I was joking. I heard the sigh.
No, that wasn't me. That was someone else. I promise you. That
Wow.
wasn't me. Someone else did that sigh sound. I didn't do that.
I did, oh, but I didn't know it.
Oh.
Yeah. Exactly. You can't have carbons with 5 bonds.
Although we all keep trying to do it.
We all keep trying, that's true, even yesterday, I was like, come on. I know.
I could, when I saw it, like, on the last test I got back, I could hear you cringing on your when it card without 5 bonds.
Through my grading,
Yes.
I think my grading is becoming more expressive of my emotions. Yes. I need to control my emotions better. Okay, that's another way. Make one of your carbons 1, whichever one, and then decide what should be on that. And then decide, okay, then where is 6, what should be on that, and so on and so forth. Okay, good. And then running the mechanism in your head, what should be on 6? Exactly, because it has a leaving group. But I want you to go back to the one you had before. Because why can't that be? Why can't the ester alpha carbon become the enolate and attack the ketone? What would that do? Let's just follow through our logic. No, that's 5 carbons.
Yeah.
You can't do that. So, but then run the mechanism in your head
Oh.
and think about, okay, if the ester alpha becomes the enolate, attacks the ketone, that becomes an O minus, but it doesn't have a leaving group, right? Aldehyde ketones don't have a leaving group. It's okay to go and help out, Dash. No, I'm just saying to other people. It's okay to go and have.
I mean, I think I have the answer.
No, the first one's correct. So, Dash, if the 1 attacks the 6, what happens to O
Which one?
for your second product, for the second approach? You showed the curved arrow of going 1 going to 6, right?
Yeah.
So what will happen to the pi electrons? There you go. So what happens to O? Becomes an O minus. Does that have a leaving group
Oh, would it become like an OH or something?
or something?
Yeah.
I don't know anything about it.
Why not?
Or would it,
And then could it undergo dehydrated, but not there? Where is the stable double bond? Not that side. It's alpha beta. It's always alpha beta because it's
this one also
conjugated.
have a methyl.
Right, it has a methyl. Yes, you're right. Now, can it undergo dehydration? Can it lose water and create a conjugated system?
Oh, yeah.
Yes.
Yeah.
So what would the product then be? Yep. Why can that happen? So that's technically not Clasian, of course, because you reacted ketone with it, but the concept is the same. If there's no good leaving group, you can't kick out anything. But if there's a leaving group, you kick it out. Yeah, perfect, great.
So would that be like a separate product?
Yeah, 2 products. Is everybody following the discussion? Yes? Okay.
For sure? Okay, well, yeah, that's fine. Okay. Okay. I'm trying to read your face right now. What's the consensus? Okay, she's just kidding, it's not right.
No, they're correct. They both are correct.
Oh.
Stop overthinking. Go with your gut. You're right, because you recognize which one lost a leaving group, so you put a leaving group on it, great. The other one uses, the one that's an ester, uses its alpha carbon. Do you all agree with the green one? Everybody okay? How about the last one, which is intramolecular? That's Dieckmann condensation. Do you all agree with that? Everybody? Okay. I'm imagining in my head everybody nodding their heads vigorously with a real great expression on their faces. At least that's how I'm imagining it. That's Clasian condensation. Questions about Clasian condensation?
It's beautiful.
It is beautiful, yes, I agree. Okay, we are kind of getting to the end of this chapter. There are just a couple more reactions for us to talk about, and then we're done with this chapter. And that means one more chapter, which is, what week is this?
7.
Oh, so next week, Monday is a holiday, so we have only one class day. I think we can finish it. That's 8. Oh, good. So that gives us a great amount of time to then practice and review and things like that. Okay, cool. That's good. Oh, I did need to talk to you guys, oh shoot, I totally forgot. But Mar is not here and, okay. Vincent, Mar and Carter, would you guys make sure they get this information, because this is important. So, oh, cool, hi Mar. Show of hands, all of those who are actually presenting a poster for their biology cure. Is it everybody? No, I thought there were a couple of people who aren't. Okay, but you don't get to escape say now. So, everyone, whether you are presenting or not presenting, needs to sign up for a couple of demo tables. The Indigo lab that we will do in the last week, we will actually create a demo table for that for 5th graders. Do you guys know about the 5th graders coming? Okay, so Say is actually a 2-part event. One is the presentation, the posters and all that EVCC students will present, which you guys will do through your. The other is more of an outreach event where 5th graders from a couple of different elementary schools come as their day out, and then there are lots of demos. Biology does a lot of demos, physics does a lot of demos, engineering too, and we do as well, chemistry does as well. So the favorite ones that have been for us, because the kids love it, one is the Indigo lab that we will do, because they get to tie-dye and get creative. And the other is the nylon lab that we are going to also do. So we will create 2 demo tables, one for nylon, one for the Indigo lab, where I need at least, and Maxie did say she will have some of her Gen Chem students also help at those tables, but I need you guys to be the leads, because we would have done those labs just the week before. We would have done nylon the week before, we would have done Indigo the week before, so you would know exactly what's going on. So I need OChem students, you guys, to be the leads on those tables. Gen Chem students basically help you out and whatever they need. So Maxie is going to create a sign-up sheet. I think the timing is 1 p.m. through 3 p.m. So we need to have about 30 minutes, maybe 20-minute shifts, 2 to 3 people per shift, so that you guys are helping out those. Make sense, everyone?
What day
Yeah?
is it?
Say again?
What day is it?
Tuesday, June 10th? Yeah? But aren't you in Bali? Okay, now you are in Say though. Sorry, I dropped that.
Yeah.
So the 3 of you guys are not in bio either? You are? No. So 3 of you, but you are still participating and enjoying the day's activity. It is fun. It is a lot of fun with everything going, plus a lot of food. So
Ooh.
yes, yes, good food too. I mean, I think I don't know what I ordered this time. But the point is, everyone needs to sign up. Once I have the sign up sheet, Maxie said she will give me a sign up sheet. Everyone needs to sign up at least for a 30-minute time block. And yes, multiple people can be at the same time, which is actually a great thing. But for both tables, vertical, not vertigo, what is it? Indigo and nylon tables. Okay, make sense, everybody? And at the end of your shift, you're going to find Maxie or some other teacher. If I'm there, I might be there for a little while. I'm not 100% sure. We'll see how things go. But you got to get some kind, I think they're going to have some kind of a paper that says, yeah, so-and-so worked at this table from this time to this time kind of thing. And you get it signed by either Joe or Maxie or Matt or Ricky. Ricky might be there too, or I, if I'm there around too. Just make sure. Everybody got it? Cool. Okay, let's talk about the next reaction then. The next reaction is something you've seen before actually. We are just giving it a name now.
Davina.
Yeah, oh sorry.
Hi.
So-
So it's one shift at either table, not one shift at both tables?
That's a great question. Let's see what Maxie needs.
Okay.
Maxie and or Joe, because they are doing the planning this year. I'm not really involved so much in the planning part this year. So probably one is what I'm thinking. We just need both tables to be manned by OChem students primarily as lead. Gen Chem students just to help out, because they would not know what this lab is about, but we hopefully do. Yeah, so let's be a bit flexible on that. Yeah. As I find more, I'll let you know. Anything else? Cool. Also, the posters, aren't you guys presenting them in groups? So maybe when you also sign up, you probably want to sign up in such a way that not all poster members are away, because you do want at least someone to be by your poster, because when people come by asking questions, there should be someone by there, right?
Yes.
Okay, the next reaction is, as I said, we've seen it before, we are just giving it a name now, and that is called Michael's reaction. I just want to make sure I get the spelling right. Michael's reaction. So, do you guys remember, I don't know if it was the previous chapter or the chapter before that, if there is a conjugated aldehyde or a ketone, conjugated means there's a double bond that is in resonance with the aldehyde or ketone, do you remember where does Grignard go?
It goes to
The
the
two,
carbonyl.
1-2 position.
It goes to the 1, 2, and of course when you do acid. So Grignard goes here, proton goes there. Agreed? So that is a 1-2 addition. Isn't that right?
Yes.
Okay, cool. Do you guys remember, oh, what am I doing? Sorry. There we go. But what about if there is a organocuprate? Where does that go?
It goes to the 3-4.
1-4.
1, 4.
Something like that.
1 is the oxygen, 2, 3, 4. The end of the conjugation. But what does that end up creating when that happens? What does that end up creating? It ends up creating an enol first. Do you guys remember that? Yes?
Yes.
But then what happens to enol? Enol tautomerizes, makes the aldehyde or a ketone. But the point is, Grignard attacks on the carbonyl carbon, but the cuprate attacks the conjugated system, the conjugation end, right?
Yes.
Michael reaction is similar to the second. Instead of organocuprates, instead of Gilman reagent, if you had an enolate, enolate also attacks 1,4. That reaction is called Michael reaction. So Michael reaction is, specifically speaking, a conjugate reaction of an enolate to a conjugated aldehyde or a ketone. So for example, let's say for example, if I have that, again, it's a conjugated system. And if I am reacting this with an enolate, where would the enolate attack? So far, all the reactions we've seen, the enolate has attacked the C double bond O because there was no conjugation. But now, if there is a conjugation, enolate does not go there. If there is a conjugation, enolate attacks at the end of the conjugation, just like the organocuprate, which then, of course, what does that create? So when that happens, it makes O minus, 1, 2, 3, 1, 2, 3. Right?
Yes.
And then if you protonate it, if we protonate this, what would happen? It would make an enol, right? And what happens to enol? Come on guys, what happens to enol?
Tautomerizes.
Tautomerizes. So where does that proton really end up? It ends up on C2. So here is your 1, 2, that part. The new bond is on the end of the conjugation, and the enolate, which is not an enolate anymore, is there. That is called Michael's reaction. So it is a conjugate addition of an enolate to an alpha, beta unsaturated aldehyde or a ketone. Does that make sense, everybody? At least as a general idea. Okay, so then let's look at some specific examples, and we'll write mechanisms as well. So, Michael reaction is really best, actually, when the enolate, it's best if the enolate comes from a system that has very highly acidic hydrogen. So it's really best to do Michael not with any enolate, but specifically an enolate that comes from a very acidic hydrogen because of two C double bond O's in the beta positions relative to each other. So, such as this guy. Right? So, let's see. So let's see what's going to happen. Let's go step by step. What do you think will be your first step? Right? But from where? Because there is alpha here, alpha there, alpha in the middle. Which one has the most acidic hydrogen?
In the middle.
So the KOH takes a proton, makes an enolate. Again, whichever direction you go, that's really not important. Agreed? What's happening in step number 2? Step number 2 is where Michael reaction is happening, because we have an alpha beta unsaturated aldehyde or a ketone. We have a conjugated system. So the enolate, the enolate goes to the end of the conjugated system, which causes the bond, the pi electrons to shift. So what does that give us? Oops, sorry. Did I do this correctly? Yes? Again, I'm just trying to show you the way the two pieces are coming together. The enolate attacking the end of the conjugation, the 4 part of the conjugation, creating another enolate. Good, everybody? So what's happening in step number 3? So when we protonate it, now again, it's up to you how you want to show it. One option is, okay, let's protonate the O minus, which creates an enol, and then you have to show how the enol tautomerizes into, in this case, an aldehyde. Because enols are not very stable. So you have to then show the steps of how that tautomerizes. That's one way of doing it. Unless the question specifically says, show the tautomers, and then of course we don't have a choice, but if the question doesn't specifically say, I'm kind of lazy about this, so here's another way to show it. That falls back, takes a proton. Ultimately, that proton ends up on that alpha carbon. So what's the product? The product, therefore, is conjugation. That's the product. Do you guys agree? Whichever way you show it. That is Michael's reaction. Michael's reaction is a reaction where the enolate attacks the end of a 1,4 conjugated system, creating basically a product such as that. If that makes sense, let's try it one more time. Please practice the mechanism at home. For now, just give me the product. Does anybody have the product for me? If we have time, which it seems like we might, do you guys wanna do the wall project?
The what?
The wall project.
What's the wall problem?
So, for the last couple of years, I haven't been able to do it because we didn't have that much time left over, but we used to do that before. So on that wall right there, I would create, basically I have these printed out names of different families like alkanes and alkenes and alkynes and everything that we've studied in this entire year. And then we use those colored tapes that has shown their substitution reaction or addition reaction, and we connect all families. Let's see if I have a picture from a few years ago, still saved somewhere.
Yes.
And it just goes over the entire wall. It takes a good day because everyone participates. Everyone is like, yep, let's connect that. It's an addition reaction or oxidation or whatever that may be. You guys interested in doing that?
Yeah.
Because then I have to go buy some tape.
If you can remember, what were the test scores like for classes that did?
They were good.
They were good for classes that do that?
No, yeah, I mean, what does that mean?
Like, usually Ricky says like, oh, like students who didn't, like, a class that didn't do this showed like.
Ricky's,
It's
it's fun.
He said made
Yeah. It's about, in my opinion, when you do something like this, it helps us look at everything we've learned from a different perspective. And that always helps, right? That always helps in creating that mental picture. But if you're interested, then I'll start the prep work. But then I need everyone to be participating. It's not like two people are there and everybody else is just sitting and watching. No. Everyone is there because I have to get a ladder. I have to get a printout. I have to get tape and everything. So tell me, are you guys interested in doing it? Then I'll do the prep work.
Yes.
If you're not in, but then as I said, I need commitment from everybody. everyone has to actively be there at the wall, and I'm sitting here and watching.
You're sure in a class day, right?
Yes, 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 a class day, yes, yes.
We're gonna be in here for final exam.
Yeah, but that won't help you, don't worry. It doesn't have answers on there. And then we also need to leave at least 2 classes for ACS practice also, so. Okay, cool. Do you guys agree? Is that right? So basically, this carbon is connecting to that carbon. Isn't that right?
Yes.
So 1, 2, 3, 4. Yeah, perfect. Please do write a mechanism like there and make sure you understand how. Okay, next reaction, which is actually a combination of 2 that we've already seen. It's actually quite cool, in my opinion. And that is called I do remember though, oh, this must be before COVID then. The last time I did it was before COVID then. Yeah, because I do remember the last time one of the students, I have a picture and all to prove it, he's actually a doctor now. He's gone through his med school, went to UW, finished his med school and everything. So, yeah, very interesting story, Sean, very interesting story for Sean. But anyways, coming back, Robinson's annulation is, by the way, the word annulation, FYI, just means ring formation. The word annulation means a reaction that creates a ring. In this case, the ring will always be 6-membered. In this case, there is no other option. And I'll tell you why, you'll hopefully see why. In this case, it will always be a 6-membered ring that will be created. Now, this reaction is a combination of 2 reactions. First, Michael reaction. First, what happens is Michael reaction, which we just saw. Once Michael reaction has happened, the second step is intramolecular aldol condensation. Combination of the 2 in this order is called Robinson's annulation. So 2-step process, in the end, creating a new 6-membered ring. So let's look at an example and see how that's working out. So, for example, if you have so first is Michael reaction. So what will be the Michael reaction product? If you just think about the Michael reaction, what would be the product? So basically, the alpha carbon is going to connect to that carbon, right? Conjugate addition to create the Michael product. So the Michael product, not writing the mechanism, I'm just showing you the product. So 1, 2, 3, 4, 1, 2, 3, 4. Do you agree? Then intramolecular aldol condensation to create a 6-membered ring. Where is that happening? 1, 2, 3, 4, 5, 6. That's why it will always be a 6-membered ring, because 4 atoms are coming from the Michael and then we are providing 2 in the second step. So it will always be a 6-membered ring. But what does the product look like after the intramolecular aldol condensation? That hasn't changed, right? What would you expect between 1 and 6? Anybody? a double bond. It's a condensation. It's aldol condensation. So what would I expect between 1 and 6? A double bond. What am I missing? So basically, if you were to think about how did these two pieces come together, this came from here, right there, and this piece is that whole process is called Robinson's annulation. Yeah.
So say we like got this on an exam,
Yes.
how would I know that it like would do both of these and not just Michael's reaction or something?
Say that one more time. I'm not sure I followed your question, Jessie. You're saying, how do you know it will go all the way?
Yeah.
I see. If there is basically the possibility of intramolecular aldol. That's it. If this weren't there, if these are not there, then you can't do anything, right? For aldol, you need 2 aldehydes or 2 ketones for aldol to happen. Specifically in this case, to make a 6-membered ring. So your hint is that this is happening is the fact that there is a C double bond O, 1, 2, 3, 4, 5, 6. It can make a 6-membered ring. It will, you can't stop it. This is not isolated. This product is not isolated. Does that answer your question? Kinda, sorta? So the point is, how would you know to go forward and not stop it, Michael? Is there a possibility of an intramolecular aldol to make a 6-membered ring? If the answer is yes, you gotta go.
Okay.
If the answer is no, then you can stop. That's it. Okay, so if this makes sense, let's try it a few more times. Please tell me, why did I do that?
Are we gonna write a mechanism for one?
Well, we already wrote it.
I think I'm maybe missing something.
Okay.
Where
Where?
you get the enolate,
Yes.
the first time, and then you get the attack.
Yes.
And then, on my paper, I still have it as before you get to here. I think I'm probably missing something really simple.
Yeah.
But, I have this.
Oh, that's the enol. Then you're going to, of course, okay, I see what your problem is.
Okay.
When I write NaOH, can we just assume
Oh, it has
it's
water in
aqueous?
it. Yeah. Okay.
So
I
just
knew
like
it was
any other case, right, it's going to take a proton, become an enol will tautomerize. So at the end, you're going to get this,
Yes, that makes sense. The
which
water.
then makes an enolate and yeah,
Okay.
absolutely. Okay, let's try this one. Let me figure it out first. Okay, got it. What would that make? Last reaction. Let's finish this. this one doesn't have a name.
Oh.
Is that you, Pran?
Yes.
See, right
It's
here.
a, I don't know.
Do you all agree with this answer?
I got something else, but
Let's see what you have. Please.
which one is this? Maybe I'm not saying.
Isn't it the same? No, it's not. No, it's not. What is it? No, it's not. I'm talking to myself. So, I see.
Can I show you where I got?
Yeah,
that?
please, and I'm trying to figure this one out too, because you created Michael product. That. And then, which is the same, right? We both have the same. So, because it's so symmetrical. Because I see, I can see that. Sorry, I'm processing. Isn't it the same?
I wanna say it's, but if maybe it's wrong, is the different double bond here?
Yeah, but should it be the same, because this is so symmetrical, no matter where you do it. Okay, so let me process. So, we both have the same Michael product, right?
Yes.
No, we do.
Yeah.
Right. Okay, so right there is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, that's that. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, so you got this.
Oh, we just used,
So here,
Just use, yeah, it's the same thing.
is it?
Because, she kept the different double bond and I got rid of the other, you know what I mean?
No, I don't. do you mean? I don't think they're the same.
I think that maybe
They're
the double
structural
bond,
isomers.
maybe the double bond is in the same spot.
maybe the other one should be over here.
Oh, no, the double bond should be here. I think that's not right, okay, yeah. Okay, so let's process this. We have the same Michael product, right? I know where the difference is. Okay, I got it, where the difference is. What Jasmine did, let me confirm first. Yes, what Jasmine did was, in the second step, the intramolecular aldol step, you created this enolate. That's your carbon 1, 2, 3, 4, 5, 6. That's how you cyclized it. Because I can see that the enolate is here, which means the enolate is there. Which is fine, great. I think what you did though, Camilla, is you, that's 1, right?
Yes.
That you made an enolate there.
Yeah.
And then you cyclized it here.
Yeah.
That's why you meant, which is why it's giving you a structural isomer. Is one better than the other? The answer is, let me think. In both cases, we have, no, I don't think so. I don't think so. In both cases, we are creating enolate from a ketone, right? In both cases, you're ending up with a conjugated product, so stability wise also there is no difference between the two. In both cases, we are deprotonating a methyl hydrogen, so it won't matter. The answer is no, it doesn't matter. I think they both products are probably possible, but do you see the difference? I was talking I was thinking aloud a lot, so I don't know if that really made any sense. Those are structural isomers, those are not the same products, but that's why they are slightly different. But they're both okay. How about those? Let's finish those, please. Looking at yours, you seem to have lost a carbon. Where did it go? 1, 2, 3, 4, 5, 6. No, you haven't. Wait. Oh, I see. Ooh. I'm talking to myself. Ignore me. May I see some answers on the board? So by the way, this is the end of chapter, whatever those chapter numbers are, I can't remember. I think there's only one more chapter that is left for us to go over, to work on, and that's the amines chapter. That's relatively small. We're not doing a whole lot in there. So I think we can finish it in one day. At least we'll see how things go next week on Wednesday. We have a quiz, don't we? On Wednesday? Okay. So 22 and 23 are done. As far as I'm concerned, I don't like the enamine Stork reaction. I hate that. So quiz on Wednesday. What is it going to cover? Oh, that's a lot.
Oh, we just don't do it.
Don't do the quiz? You all get 0?
Oh, no, that's not what I meant.
What? If you don't do it, you get a 0, don't you? How does the math work?
No, I meant like, we all collectively don't do it.
If you collectively don't do it, you collectively
It was a
all
joke.
get
Wasn't thinking
0.
to it. It was a joke.
It's a free country, Dash.
Huh?
It's a free country. Nobody's making us do anything. How about we just do chapter 23 then? Is that okay? Only chapter 23, which is a lot too. I mean, it's aldols and Clasian and Robinson and all of that stuff. So let's just focus on chapter 23 for the quiz on Wednesday. And as I said, we will try to finish amines also on Wednesday, which means we'll be done. And then we'll start working on. So you guys are still committed to the wall project? Okay, then I'll start prepping for that. And then we will also we'll get good amount of time to actually practice ACS then, do reviews and practice. Good, okay, cool. That's good.
So just, is it not going further?
Say again? Oh, did I miss something? Yeah, I did miss something. Yeah, I guess it will have to stop. Yeah, I missed it. That's on me. I was trying to be fancy. It is not fancy. Could you take out that second pH? Erase that. No, yeah, that one. What would that do? What would happen? Make it enough. Yeah, you're right. Okay, so for this one, let's see. Yeah, and then 1, 2, 3, 4. Yeah, exactly. So this is where it's coming up. Yeah, I agree. So this is, again, that's the reactant over there, and this is coming from the conjugated system, same thing. Right there. Yep, absolutely. So we have. Oh, I see. Then where's your C double bond O? You're missing one C double. Where is this C double bond O? On carbon 2. Shouldn't that be? Yep. How does that feel? How many of you have, like my brain is like, my eyes are like, what's that? I'm going cross-eyed almost. Trying to figure out where. But this is Robinson annulation. So we are ending chapter 23 with this reaction. Chapter 24 is the last chapter, which is the amines, which also I think we will just cover select parts depending on what's needed. Any questions? Yes, please.
Do you make the RACS?
No, ACS is made by American Chemical Society.
Okay.
And so it's a national society.
Okay.
And many schools, not just community colleges, but lots of universities take it. So it's a really nice way for us to, what's the word, compare ourselves to the rest of the nation who's doing the same course.
Okay.
No pressure, actually we've always done way better than the average. We've always done way better than the national mean.
Oh, is that it?
Okay, cool. See you all on Monday, Tuesday, right? Tuesday. Lab. Oh, this is the last serious lab of the year, aldehyde enigma. Which, again, please let Carter and Mark and Vincent know. This is a lab that is going to be done in pairs. You will do it with a partner. I'll talk more about it on the day off, but you will do this with a partner. And it's one of those labs that you don't ask me any questions. Come on, let's figure it out. Kind of lab. There is lots of NMR and IR in it, so please also review, make sure you're prepared. Of course, the first day I don't expect anybody doing spectroscopy. I think the first day is probably just doing the reaction and spectroscopy on the second day. But we'll see how it goes.
Take a chance.
Cool. Yes, we are finishing up this, which is spectroscopy, and you know how it is so much dead time during spectroscopy. The rest of the indigo and nylon those are fun labs. Mix, here you go, let's have fun with this, let's get creative and that kind of, so those two are fun.